No, I just started it. And it probably wouldn't pick up audio all the way over there anyway. Question?
Yeah. Did you get my email about the GC problems?
I don't think I did. Oh, from like a week ago? I did, but yeah, I haven't forwarded it on.
Okay.
Oh, yes, I did forward it on, and I got a response, and then I never followed up. So I apologize.
No, it's okay.
Is it getting better?
No, because I was trying, like, I've been trying to press this, and I would go to download it, and it just, nothing happened. And I have, like, three different...
But you had it downloaded before, right? The most recent version?
Yeah. And I have 3 versions now because 2 of them don't work, and then 1 sometimes works.
Did I get you guys the permanent license?
No.
No, we're still on the temporary license.
Temporary.
All right, I'll email Dr. Thompson and we'll do permanent license, and then you can erase everything off your machine except your files, and then we'll try that and see if that works.
Okay.
Okay, how you guys doing? Tino, how you doing? Are you ready to start? Did you start on the next assignment? Hopefully you've dug into that and started working on it. If you didn't, I hope you have some time in the next few days because you need to carve out the time for that. Hopefully you've got some start. But I'm going to show it to you and we'll talk about it. But the first thing I want to do was, we're kind of on a 2-track journey here. One track is we're building tools for making animations to be didactic objects, right? So as we do more and more GC assignments, we're kind of like adding to our repertoire of things we can do to create animations, right? And the other thing we're doing is we're kind of also on this track of like learning calculus in a conceptual way, right? Like the ROC calculus. And so those are going to like converge right pretty soon, like very soon, in the next week or so. Those are going to converge and those will be the same. So what we're doing is, as we're learning the calculus, then you're going to be making GC animations that are supporting that endeavor of understanding calculus. So it'd be like didactic objects that you would use to teach the calculus that we're learning. Does that make sense? All right, great. So what I'm going to do is just do a summary of what have we done so far. What are the tools we have so far in terms of making GC animations? So from the beginning, we emphasize So at the beginning, we really emphasize defining functions and using function notation. Function notation is, and what is function notation again? What's an example of function notation? What does that mean when I say function notation? What's that?
F of x.
Right, f of 3, right? G of 8. G of 8 plus h, right? So in function notation, what does it represent? Values of the independent variable or the dependent variable?
The independent variable, using.
But when you write a whole statement of function notation, dependent or independent? It's the value of the dependent variable, right? And it's the particular value of the dependent variable when the independent is what you see in the parentheses, right? So that's and then GC, GC works just like that. So you can use function notation to stand for values that you want to call upon a function, right? And then you can make formulas and graph things using function notation. So this is huge. Defining functions using function notation. All right, what are some other things that we've learned? Maybe can we start kind of from the beginning? What other things were we learning at the beginning? Yeah? Yeah, sure. So variables and parameters. So, free variables in GC for parameters, variables, function names. Okay. So we learned about how there's any free variable in GC, any letter that's free, quote unquote free. It doesn't have a specific meaning. You can assign it to be a parameter, a variable, function name, a constant. Okay, and then also, so we learned about assigned. Yes, hold on to that thought. That's a good one. Assigned letters in GC. What are some of the assigned letters in GC? Things that already have N is a good one, right? The slider opens up the built-in slider. X and Y for graphing, right? But in a function definition, so actually, in a function definition, you can use anything for the dummy variable. Okay? But in anything else besides a function definition, these assigned letters are going to take on their built-in meanings. They're not free to use as you'd like. Okay? Remember, is there any others that we've come across? We did T, right? T is the parameter, built-in parameter. All right? So pi, E, okay, what other tools have we? Someone said constant rate of change, right? So constant rate of change. And along with constant rate of change, what have we been doing recently? But based on constant rate of change, we developed what? The lines, right? Right. It's our point rate form of a line. That's going to be a super important. You still read that? Okay, what else? What other things have we learned? So that falls under the constant rate of change, point rate. Yeah, so that falls under that umbrella. Okay, good. Piecewise functions. That's good. Using control A to split up piecewise function. Good. What else? Okay, to do what? Yeah, graphing. Graphing, right? So graphing, what do we graph? Do we graph functions? Oh. Functions. Functions, oh, yes, functions over intervals. So this may be what you're talking about with the inequalities, right? Functions over intervals, lines, points. Another big one in graphing that we've done. What else have we done? What's that? Yeah, sure. So absolute value for reflections. That's what we can do that. Yes. Important. Very important, right? Regions also uses inequalities, right? So like we're shading regions. This is going to be huge for doing animations. Okay, if we think of more graphing stuff, we can come back and add to that list. Any other tools that we've acquired? What about last time in class? We picked up one more tool. And this one is... What's that? We'll just type it out, right? So what was it? Can you just say what it was without naming it? Remember what it was?
Well, the form was like
the form.
minus t
Yeah.
times, well, it can be a function or
Right.
a value or a point, and then plus t times, I get one of those things.
This thing. And so, remember this? What? It's like the morphing.
Oh, parametric.
We call it our morphing. The morphing operator. How about that? Right? And so like we use it for a function and we set t to be n, then it only takes on one at a time. It shows you just one particular n value at a time. And so we showed how you could like morph one function to another by changing the value of n, right? But then also like you could graph a whole segment, right? The whole segment using t. Because t is like x or y, it will spray all values at once. So like if you set t from 0 to 1, then you get a when t is 0, and you get b when t is 1. And then as t takes on all the values between 0 and 1, you get everything in between, right? And this is a very versatile, I'm going to show you a good example of this that I've used. It's a very, very versatile tool. This will show up a lot. But it's my experience that students, like, because it's so new and so unfamiliar, students forget it's there, and they don't gain enough experience trying to use it, and so then they kind of forget about it. So I just encourage you whenever, if you can remember that you have this tool and try to use it. Just try, and then it'll become natural. Then when you need it, you'll be like, oh, I could use that tool. Yeah.
Are we gonna have to use that in the GC file that we're creating?
Could it help? Well, we'll talk about that.
Okay.
She's catching on.
Slowly.
She's catching on to this class, right? Okay.
Finally.
All right. Any other things, tools that can you think of that we've learned in this class? That's a lot. Okay. If that's not all, then that's most. Well, just animating with the n with sliders, right? So animating with sliders. Right? So sliders allow you to have a variable that truly varies, right? It truly varies before our eyes, and we can do all kinds of things with that. Oh, we had like, I showed you viewing window stuff. I guess that's on this project that we're doing. So we'll just put it in now. So like view sliders. So if you do a slider that's like, it's like different integers, so when you set it at different integers, you get different static views of something, rather than like an animation that's continually changing. So first I want to show this and talk, and then I want to add something, or I want to change it abruptly, or whatever. So that's like view sliders. With if-then statements. So if view equals 1, then show this and this and that, right? So or show this point if view equals 2. Show this line segment if view equals 3, etc. Okay, that's pretty good. So it's a pretty good list. So let's look at the assignment that's due Thursday-ish. Did I say Friday on Canvas? What did I say? Yeah, so I wanted to give you one more chance to ask questions on Thursday. So it's not due Thursday at noon. But normally this one's due Thursday. So but I do want to give you one more day to kind of troubleshoot with me. So we can say Friday at 5 or maybe Saturday at 5. If you need another day, that's fine. Okay. But not next Tuesday, because we're going to have another assignment for the following Tuesday. All right, let's see if I can find that. Or let me, sure, let's do that first. So this is a smartphone. Where's mine? Yeah. I think the way that I've explained the views and labels might be a little different than the way I have it. So just do it according to the instructions. But this can just be for you to get an idea of Okay, but so you're gonna have a view where you just show dz statically, and then you can change the value of z. And so look what happens. So notice when n is 0, I'm at my starting value of z, and when n equals 1, I'm at the final value of z. But if I come over here and I can change the starting value, and I can change dz. Okay, so I just changed the starting value and the amount of change. And now look, when n is 0, it starts at the beginning. When n is 1, it's the end of the change. So what happens? So according to C and D, and again, the way I've explained it might be slightly different than this. Follow the instructions on Canvas, okay? Follow the instructions on Canvas. But the general idea is you change the starting value of Z and the change, then n adapts. It adapts. N equals 0 will always be the start of dz, or your initial value of z, and n equals 1. You do the slider, and it'll finish at the ending value of dz. So, what might help to do that?
So the attachment that you put on the smartphone, right? Animated, that has, I mean, it has something to do with this, but it's not like we have to basically just make a new file.
Oh, that was just to show you. That's just to give you an example of using view slider. That's all that is.
Was really, I was like, I don't
No,
know.
yeah. So all that is to show you. So you're gonna like study that and see what's going on with with using a view slider. That's all that is. It's an example of a view slider.
So we have to make a completely new GC file for this.
You're making this. You're making this. That's the assignment.
Okay. So it's not that file.
That file is just an example of how a view slider works. So you study that file, so you figure out how do I create a slider that lets me change the view. So that's just so.
I got really
Sorry.
nervous. I was like, oh my god.
Sorry, that was just, it's just an example of, for you to study and learn how to do views. The assignment is to create this.
Okay.
The assignment, you're creating this.
Okay.
Okay, so then, so that's one thing, right? So so I've changed the starting value of z and the change in z, and now when n equals 0, z shows the beginning of the initial value, and when n equals 1, showing the ending value, right? So that's going to be a challenge to this, but again, think through the tools that you have that could help do this. Okay, and then there's another view. View 1. So then view 1 is where dz changes with z. I don't know what view 2 is. I don't think you have a view 2. Maybe my view 2 is just no dz at all. I don't know if I specified that. I don't remember. But the two key views are when dz actually changes with z as n goes from 0 to 1, and then the view where just dz is just static, it's already there to start with, and then z changes through that interval. Question?
Will you put up like a video of you messing with this stuff, or do we just have to look at the previous lesson thing?
See if the video that I gave you the time, like at the beginning of that one video, I referred you to it. If that's not enough, like that should do it.
Okay.
Oh, but no, this video I'm recording now, so you'll have today's.
Okay.
Yeah, I'm recording now.
Great.
Yeah. So you'll have both. You'll have it when I used it before, or 2 weeks ago, or 3 weeks ago, and then this is hopefully I can get. This is my first time trying the new software, so hopefully the recording will work. Okay, other questions about this assignment? So, what's the deal with these harder assignments? You've got to carve out little pockets of time. You cannot sit down on Wednesday night and say, I'm going to get this done in 2 hours. Because what happens is, I'm sure you've all experienced this with difficult problems or longer problems. You have to chip away at it. And when you work at it for a while, and then you go and you have lunch, and you do laundry, and you play, intramural sports, and then you come back to it and you look at it again, and then all of a sudden you have all these new ideas, right? And this is very common. But that's the way you have to approach these longer problems. You have to carve out little chunks of time to keep looking at it over and over again, and that's when you'll have your revelations. Every time you sit down and look at it, something different will come to you, right? And you'll make more progress that way than saying, I'm just gonna nail this down in 3 hours tonight. Because you'll come to a brick wall, and then what do, right? But if you take a break the next day, then all of a sudden you can get through the brick wall. Any other questions about this? I hope so. It's hard, this is like the first hard one, but then I hope you have this sense of pride when you get it done, right? Like, because you can do it. Like, my experience is, students, if they work at it and they, like I said, set aside lots of time, get help from me, get as much help from me as you need, email me, come find me, get as much help from me as you need. And there's like this sense of pride when you get it done. Okay.
Do we have to set it up like where it's like blank in the back and then just have that 1 to 10? And then
Yes, and that's pretty easy. So the graph, all you have to do is decide where this is going in R2 and rectangular coordinates, right?
Yes.
Where this is going in rectangular coordinates, and then just turn off the graph.
Oh.
So I put mine on the x-axis. And then once I got it, then you just turn on the axis off, and then it just floats there.
Thank you.
Yeah, sure. There's another tool that could be helpful for this, and let me just show you that. And that's like if you want to repeat something a bunch of times, say I wanted to I don't know, say I wanted to graph a bunch of horizontal lines. Like I want to create a dotted line, all right? I want to create a dotted line horizontally. And so you think, oh, that's a bunch of little segments. I could write a command line for each segment. All right. Well, that's doesn't make for a good file in the end, and that's a lot of work. So could you do that all in one line? You can. So we can say, like, so y equals 2. Okay. So y equals 2, and I want to go from So say I'm going to make them, I want to make them like 1 unit long, all right? So I'm going to go from A, so x goes from A to A plus 1. And then what I have to do, I just have to specify, my A values, right? So if I want to make them one unit long and then a space of 1 in between, then I can say, so I do a comma, and then you do control equals, so A, then control equals gives you is a member of, and then you could use the braces, which is shift bracket, and so now I'm just list out the A's that I want, right? So say I want to start at 0, so then it would be 0, and then where would the next one start if I want to leave a space? So I'm making a dotted line, so where would the next A be? Will it work if I do it at 1? Will I get a dotted line? This is right now it's going to show what? 2 from 0 to 1. And so where's the next one I want? 1 to 2. So can I make a dotted line? It goes 0 to 1, and then 1 to 2, and then 2 to 3. It'll connect. It'll just be a line, right? So what do I want?
1.5.
Okay, sure. Some space. So how much space do we want between? I said 1. If we want to put lengths of 1, yeah, so we're going to go to 2 next, right? So then you just skip 2. Like you just list them out like this. And let's make it so you can see it. That's better. So what happened?
Oh, you had 5.
Yeah, right? So you look at it and say, oh, that's not what I wanted. And yeah, it did just what I told it to do, right? It put 1 in there at 5. Just draw axes. That's I've shown you that before.
Wait, no, not the axis, you're on graph.
Yeah, there's graph paper is like the light blue and
Oh.
axes. Turn those both off. All right, so now let's suppose I want to make these really short and I want to do a lot of them. So I want to make them now 1/10 long. And I want it to go all the way across. And I don't want to type a zillion numbers here. So what I can do is I can go 0, comma, 0.2, comma, and then option, colon, gives ellipses. And then where do I want to stop? I want to stop at 50. So that's a lot of little dotted lines. Look at that. So yeah, you do option, colon. So you do the first two to set the pattern, like what your space is going to be between, comma, then option, colon. Maybe it's control colon on, and then another comma, and then your final value, and then it's going to keep that pattern going all the way to that. So look, I just made a dotted line, and it didn't take me 100 command lines.
10 lines?
Well, that's what is that?
50 lines,
That's 250 lines, right? It's 250.
Oh, my.
So this is a really powerful thing also. This tool where you can use a parameter in a statement, and then specify lots of values for that parameter. So a is a member of, and I'll just do them all at once.
How do you do the element of symbol again?
That is, yeah, for me it's control equals. Is that, yeah, control equals. So add it to your toolbox, right? If you want to repeat the same thing over and over and over again, this is a really powerful tool.
What if you wanted like a label for each of those little dots? Is there like an efficient way to do that?
You couldn't put a different label on each one. I think we might be able to repeat a label. So I could do a point, so control 2. So labels are points, right?
Yeah.
Have we done this before? So put it at a point and say at the point, well, A. So it's going to be like A. So centering it, it's going to be A plus 0.05. We'll center it on there, right? And then the 3.5. And say equals. Yeah, so we could only do I don't know if this is going to work. We can try. So label equals X. And we want the font size to be small. Font size equals, try 6. I don't know if this is going to work. Let's see. Look at that. So that's, what's that? They're supposed to be, but I don't know why are those dots there? That's weird. I see the X's. Maybe let me pick it. Let's make 16. Why are there dots? That's weird.
When do you use label and when do you use symbol?
Oh, that's what I wanted. Okay, that's why. So I guess, yes. So we're learning something, even your teacher learned something new. All right, so label gives you a dot and what you label it. So symbol will just give that, that's right. Symbol will just give that. The X. There we go. So you can do that, but you can't vary the symbol in one line. If you want a different symbol, you've got to use a new line.
Okay.
So you can repeat the same symbol.
That is cool.
So if you want to label a point, then as well as plotting the point, it'll put the little whatever you label it next to it. Okay, so we got to get to the new stuff. Any questions about the assignment? So work as much as you can before Thursday so you can get your questions answered in class or with me personally. But do as much as you can on this before Thursday. And if you're saying, geez, I really want to do this, but I don't know how to do it. Go back to our list of tools. Because everything that you need to do this is in our list of tools. Okay? And let's add this to the list here. This is what repeated elements. With parameters. So I'll call it that. I'll call it repeated elements with a parameter and a set of values, right? So I used A as my parameter, and then give it all the values for A. A is a member of this set, and then it does them all. All right, so let me show you my example of the morphing operator. Okay, so I made this file to teach radians. This is my didactic object to teach radians. And so first I show the circles, and then I show a circle. I highlight the radius on the circle of radius 1. And then here's how I use the morphing operator. So then I show that I want to take the radius, I want to peel it off its normal spot, and I want to lay it on the circle. So this was a perfect use of the morphing operator. So here's the radius of the circle of radius 4, highlighting that, and then pull it off, wrap it on the circle, maintain its length. Same thing, circle of radius 6, highlight its radius, wrap it off. I can go back. So yeah, sorry, just.
No, if it's coming from like say if you want to go from, I guess that'd be a different, map. It's like going from the axis
So that was just to show so it's the same, right? So all those, laying that arc on the circles gives you the same angle measure, right? And that angle measure is 1 radian because it's 1 radius of arc length, right? So let's see. So then I think I need the rays to be like, maybe this will do it. No, where's my rays? Maybe this will do it, I don't know. I forgot how to use it, here we go. So then I show that, then that angle is 1 radian because it's, no matter what circle, it cuts off 1 radius length of arc length, so that's 1 radian. That's the definition of 1 radian. And then as you keep going, it keeps sweeping out. And then I zoom in, and this showing these are the different radian measures here. So 6 and a little more, 6.28 radians to get around the circle. All right, so you want to see, it's pretty It's pretty hairy here. All right, so can you, let me make it bigger, but can you find the morphing operator in there? Hold on a sec. Settings. Oh, wait. Can you see it? Anybody see it? Where?
Talking about morphing operator meaning like where the T's are, like in the simplified.
So that thing that I showed you last time that we listed, the morphing operator, A times 1 minus T plus B times T.
Okay,
So where do you see it?
Oh, the A is going to be the 1 minus T, A minus 1, and then 1 minus R1 would be the 1 minus T part. Am I explaining this right? Is this what you're
So
asking?
you say, so the T value you're seeing is what? R1, so
Yeah.
1 minus R1 times this point
Which is A.
plus, right?
Yeah.
All this times R1. See it anywhere else?
Yeah,
It's here too. So 1 minus T plus something times T. So it's there. I think it's down here too. So let me just explain. This, I didn't think, when I was making this, I didn't think of this command, okay? I worked at it little by little. So I got something primitive, something that was decent, right? And then I thought, oh, I could make it better this way. And then I could make it better like this. And that's how this was formed, right? So I think part of this is, I don't remember, this was like 7 years ago I did this, so I don't even remember what I did. But I think part of this is creating the thickness of the line, creating it, like a region, right? So that's what is that? That's a region.
How did you like learn how to do this?
So experience little by little over time, like I said. So like I said, when I did this, the first thing I did is I just like had a stick, and I figured out just how to tilt the stick up without, maybe it wasn't curving, or just tilt the stick up. And then I thought, okay, so I want to improve on that. What would be an improvement? So, get it to curve as it goes, right? So how would I get it to curve as it goes? So it's like little things at a time, So it's kind of like, and again, I think I've said this before, but it's like where there's a will, there's a way. If there's a will, there's a way. Like if there's something that you're imagining, there's a way to do it. And so then you just got to believe that and keep working at it until you get it.
So is the only way to change line thickness by creating a region?
If we want to make that line
For us, yes, but no. You can. There is a thickness command in there, but you don't know about that. No, but I mean, it's better that you don't have it, because then you have to rely on the mathematics, right?
Yeah.
This class is kind of like programming. Yeah, that's why.
But it's not, because these aren't computer command lines, right? These are mathematical statements.
Like programming your mind.
That's different, right? But it's not computer programming, right? We're not learning a computer language. We're just learning mathematics. And if you give GC the mathematics, it shows you what you gave it. So that's why this is such a great teaching tool, right? So also like giving your students projects to do, because then they're forced to understand the mathematics that it would take to build an animation. We've talked about that before too. So that's what makes GC such a powerful tool. Not only the things you can make as didactic objects, but you can give it to your students to either analyze or make up their own stuff, like we're doing in this class. You've got to know the math. You've got to have the math down to be able to do it. All right. Oh, look, and I used that too. So here, this is how I did the thickness, I think. Yeah. So that's the 4, that's the radius 4, and that's the radius 6. Okay, but this was complicated. Again, I didn't just sit down one day and build this, so that's why I want to encourage you. It looks overwhelming, right? But I just did a little bit of time, like I did what I could, and then I said, how could I improve it? You know, and so then I added a little bit more. Okay? And then over several semesters, this became what it was. Yeah, this was not, like I made it and I used it, and then I came back the next semester and I'm like, yeah, this could be better if it was like this. So I worked on it some more and I improved it.
Oh my god.
Yeah, and it's really helpful for teaching radians. Right, what is a radian? A radian is, it's the amount, it's the angle measure that cuts off what? Exactly 1 radius length of any circle, right? It's the amount of openness of an angle that cuts off 1 radius length of any circle. Right? That's what a radian is. Okay, cool. Pretty good. So, like I said, dig into this project as much as you can before Thursday, and we'll answer questions. I do not want to save that. That's all in the video. All right. So let's talk about calculus. So we said dx. We said it was a change in x. And now we're going to say it's a little change in x. So we'll call it the differential, right? So dx is called differential. So now we're going to say that dx is a little change. But it's still variable, right? We talked about how dx is variable, right? It's going to vary. Dx varies. So even though it's small, it's still a varying quantity. Think of it as varying quantity. All right, so, and then for related variables y and x, talking about differentials dx and dy necessarily implies constant rate of change. So if you're talking about dx and the resulting dy, that implies that you have constant rate of change, okay? So what will be the relationship then? Or what is the equation that says that y and x are in constant rate of change? You're all thinking it, right? Y and x are in constant rate of change, then y equals mx, right? Charlie? dy equals mdx. Remember the trip to California? We said y equals mx doesn't necessarily have to be true. But if you have a constant rate of change, you definitely have dy. There we go. dy must be a constant multiple of dx, right? dy equals mdx. And that means that what? It means that y and x are in constant rate of change? Or dy and dx are in constant rate of change? What do you guys think? Remember from the California trip? Does it mean that if dy equals mdx, then dy and dx vary with constant rate of change, or does y vary with constant rate of change with respect to x? What's that? No, you guys, no. The whole point of that was that y varies with a constant rate with respect to x. In order to show that, you have this relationship over their changes, right? So this is, that's what we said. If y varies at a constant rate of change with respect to x, then, or if and only if, dy equals mdx. That was the big takeaway from our trip to California, right? Our road trip problem. Y varies the constant rate of change with respect to x, if and only if dy equals mdx. So if you have constant rate of change, then dy equals mdx. If dy equals mdx, then you have constant rate of change of y with respect to x. Okay. So let's talk about Usain again. We're going to skip this part. So we've talked about this. Did he run at a constant speed the whole race? No, right? He has to speed up at the beginning, and then he's going at his peak speed, and then actually right at the end he slows down a little bit. So what does it mean that, here's a new question, what does it mean that 1 second after the start he was running at 13.754 miles per hour? So what does that mean? At 1 second after start, he was running at this speed. What does that mean?
If he were to continue running at that exact same speed the entire time, he would cover for every 13.754 miles that he covered, he would have ran an hour. Wait, or is it the other way around? For a change in 1 hour, he would have ran 13.754 miles. There would be a change in 13.754 miles. Sorry, I'm trying to like word it.
Oh, yeah, you're getting there. You're almost there. It's great. It's really good. So you said that if he were to keep running at that speed, then for every
change in 1 hour, he would there would be a change in for every 7.54 miles ran.
Okay, so every hour that he runs, he'd go that far, 13.754 miles. But what was our broader definition? For any change, right? So for any change in time, his change in miles would be times that change in hours. Okay, so that was good. So that's good. So that's if he keeps running at that. Does he keep running at that speed? No. So how can we still use that? Can we still say the same thing, but kind of hone it in so that it's actually not that he keeps running at that same speed? So can we still say that same thing for a change in time? Can we say for any change in time, his change in distance is 13.754 times the change in time? Can we say that?
Maybe if we're looking at between 0.95 seconds and 1.05 seconds.
What about that? What about if we took a really small amount of time at the 1 second mark, and now let our changes in time be within that? So he's saying like between 0.99 and 1.01 seconds after the start. If you let your change in time be within that interval, could you say that his change in distance was 13.754 times that change in time? Or really close, right? Or really close. Yeah, so we can use that same, our constant rate of change, just as long as we have a small enough interval of time. Then within that interval of time, we can apply the dy equals mdx. We can say his distance ran is that 13.754 times the change in time, as long as that change in time is within the little interval. So that little interval is what we're going to call a moment, all right? So a moment is a small enough interval of time that you have constant rate of change. Right? Because if you think about any curve, what happens if you zoom in on any curve? If you zoom in enough on a curve, what happens? What does it look like? Straight line, right? So once you you zoomed in far enough to see a straight line, then you have a moment. You see? You have a moment because you have constant rate of change. How are you doing? Is this making sense? Okay. So that's what we're calling a moment. A moment is like, it's a short enough interval of time so that your function is linear and you can apply constant rate of change. So a moment is a small change in the independent variable variable, period. Dx is not equivalent to a moment, right? So dx is going to be variable within a moment. Dx is a little change in time within that moment. Dx is, remember, dx is like, we're allowed to pick different dx's, right? In constant rate of change. For every change in x, for every dx, the change in y is yada, yada, yada. So we've got to give ourselves some freedom for dx to be a different amounts of change in x, and that's within this moment, this interval that we're calling the moment. Does that make sense?
What defines like a small change though?
Small enough so that if you zoomed in on the graph, it would appear linear, right? So you zoom in far enough so that you have it's linear instead of curved.
Isn't that like infinite though? Like
Right. So there's this idea in calculus of what's close enough, right? So once you get to the point, you're like zooming in on something, and once you get to the point where when you zoom in, you keep zooming in, it's not changing anything, then we just call it a day. We say it's close. It's so close that we don't know the difference. That's the idea of limit, right? That's the idea of limit, that your approximations are so close to each other that it doesn't make sense to go any smaller.
okay.
Is that okay?
Yeah.
Yeah.
Talking about it, yeah,
Yeah, sure. Okay. No, it's good. It's perfect. It's the right question. Because you're right. Technically, it's never truly constant rate of change. If it's like this curve, his distance is a curve, right? His distance time graph is a curve. You're right. Like technically, it's always curved. But it's kind of like if we split hairs enough, there's this point where it's so close that it doesn't make a difference, right? They're so close to each other, these approximations that we're using, that we call them all the same. Okay, so a rate of change at a moment exists if there's a small enough interval in which the rate of change is essentially constant. So this is what we talked about. If you zoom in far enough on a curve, you'll see a line. And so that's the rate of change at a moment. But there are functions that if you keep zooming in, it never straightens out. So we don't have time to look at those. Those are really super cool. But there's functions that you keep zooming in, and it keeps staying jagged, no matter how far you zoom in. So a rate of change at a moment would never exist for those functions. But those are very special kind of anomalies, right? Those are, when we're talking about speed and acceleration and things in the real world, normally they change continuously, and then you have rate of change at a moment. Okay, any questions? So let's apply. So the constant rate, that 13.754 miles per hour, that is his speed at the moment, 1 second into the race, like Charlie said. What about if we looked at from 0.95 to 1.05? Right, that's the idea of a moment. Then we can apply constant rate of change. For any given change in time in that moment, the change in distance is 13.754 times that change in time. But only within the moment. If you go to the next moment over, then you have a different constant rate, right? So if you go over to 1.05 now, 1.05 to 1.15, you may have a slightly different rate, but then within that moment, you can use that rate. Okay, so here is his distance time. So function f relates Usain's distance from the start to the time since the race started, independent. So I'm showing that graph there. This is the displayed graph near x equals 1. And it's essentially linear from 0.99 to 1.01 seconds. So imagine x increasing from 1 second to 1.006 seconds. Simultaneously, his distance changes from 3.4882 meters to 3.5251 meters. What is his speed at the moment x equals 1 second? So just before we get into the activity here, how would you do that? So if the time increased from 1 to 1.006, his distance increased from 3.4882 to 3.521 meters. how would you calculate his speed at the moment, 1 second? What's that? Divide what?
3.5251
Take 3.525 divided by 3.4882.
No. 3.5251 minus 3.4882 divided by 1.006 minus 1.
Right, we'll take the change in distance.
Yeah.
The little change in distance over the little change in time will be his, what, speed at the moment, right? So we can consider it a constant speed in that small interval. Okay, so here it is. Here is, we're zoomed in now. It's the same graph, zoomed in at 1. So I'm showing from 0.99 to 1.01. And it looks linear, right? This is the same graph. So we can consider this to be a moment, and we have constant rate of change at the moment, right? We have constant rate of change at the moment. Yeah?
So since it's a really small change in time per moment, we wouldn't look at it as an average rate of change?
It is an average rate of change because we're doing like change in distance over change in time. But how do we get instantaneous rate of change? Like, how do we get that? Well, we get it from an average rate of change over a very, very small interval. That's where it comes from. Because you can't get a rate of change unless you have a little bit of change, right? If you just call it like, what's the speed at 1, and there's no change in time. I mean, like, how fast is he in that picture? How fast is he running right there at that moment? How fast is he going in that picture? Is he moving in that picture? He's not moving in the picture, right? Because it's showing you an instant, right? It's showing you an instant. So in order to have speed or rate of change, you have to have a little bit of change. And that's what an instantaneous rate of change is. It's still an average rate, but just with a small enough interval that if you make it any smaller, you won't get a different result. That's the idea of limit. Does that make sense? Cool.
It's kind of like finding like approximate.
What's that?
It's kind of like finding approximate limits that that came from the same kind of method, like because you just take every value that's close to that.
Right.
And then
Right, and so the limit itself is when you get close enough that your approximations don't change anymore.
Yeah.
Except if you take it out to 100 decimal places or something, or 1,000 decimal places, right? You get to that point where your approximations don't change, well, that is the limit.
Yeah.
And that's what we call the exact value.
Okay.
Yeah. Okay, so here is, I'm showing dx within this moment. Like I'm showing the moment. The moment is like the whole interval that I'm showing over there. And then I'm showing dx and the corresponding dy. So I'm gonna have you fill out this table, okay? So for each item below, you're going to identify the value, meaning the number, right, like 5 or 6.8 or pi, how it's represented symbolically, and how it's represented on the display graph. Okay? So go through this. So we're really understanding the situation by identifying all these things. So we're going to go through items 1 through 6. What are the values that characterize these items? Symbolically, how do we characterize them? And then on the graph, how do we see it on the graph? Can you work together? Okay, go. Okay, you want to go through them? Because I got one more screen like this. All right. So the initial value of the independent variable. What do you think? What's the value? 1. 1 second. Symbolically?
It's 1 second since it's 7.
But so what symbol do we use to represent the initial value of the independent variable? Yeah, so symbolically, right? It means what symbols do we use?
I thought you meant like metaphor, like, you know.
Mhm. Was it? So yeah, so like x initial or x sub I, right? X initial, x sub I. All right, so what about the initial value of the dependent variable? 3.482 symbolically? Oh, I heard someone saying it over here. Yes, f of 1 or f of x initial. Yep, f of 1. F of 1, right? Remember function notation, right? We're going to use function notation. Differential in x is? Differential in x? No, that's the width of the moment, right? So what dx are we talking about here? Yeah, so it's like in the how it's showing, right? So within the moment, this is what it means. Within the moment, dx is varying within the moment. This is showing dx here. Okay. Dx is the horizontal arrow. And then symbolically, dx, right? The differential of f?
Or sorry,
It's dy symbolically, and what's its value? Anyone get it? Point oh something, point oh or 0.1 something, 0.0368. It's dy, okay, or df. What's the moment in question? Right, the interval from 0.99 to 1.01. Or you could, if you want, you could say 1 to 1.01, right? So there's no like right answer to this. You could say 0.995 to 1.005. Or 1.01, right? So it's like any interval that contains our dx that's small enough could be a moment, right? So there's like no right answer here. We don't really have a symbolic notation for this. Okay, and then what's the rate of change? What we said at the beginning, right? It's the change in y, so it's going to be dy. So what's symbolically the rate of change is? dy over dx or m, right? dy over dx, in this case df. We're using f to mean the y values. df, dx, or m. Okay, questions on this? So the next one is a little, I want to make sure. Any questions on this slide? All right, so function f, here's the same thing again. Function f relates Usain's distance from the start line, dependent variable, to the time since the race started. Usain's speed at the moment x equals 0.4 seconds is 3.05 meters per second when its distance from the start is 0.702 meters. Answer 1 through 7 below pertaining to x equals 4.408 seconds. Go. Who thinks they know what the moment in question is? Or possible answer? Go for it, just shout it out. Yeah, let's do 0.4, something bigger than dx, right? So when it's like something bigger than dx where we know we have constant rate of change. So how about from 0.4 to 0.415? That works, right? But you could say 0.395 to 0.41. That would be an acceptable answer too, right? So any interval, we have constant rate of change that is big enough to have your situation in it, okay? Where your dx is. Okay, what's the rate of change at this moment? Symbolically, it is dy dx or m, and what's the value? Gave it to you this time, right? 3.05. Cool. Key values of the independent variable. Symbolically. X initial and X final, right? And X initial, X final. And what are their values? 0.4 and 0.408. Okay. Differential is dx, and what's that value? 0.008, right? 0.008 seconds. Everything good so far? What's our differential in f? So two ways symbolically we can say this. So what's one way symbolically we can say the differential in f? df. But what also now? Okay, yeah, that's true, and so I guess it's three ways. M dx, right? M dx. And so what's this value? You calculate it, right? You take 3.05 times 0.008, and it turns out to be 0.0244 meters. Okay? Initial distance from start? F of 0.4, right? F of 0.4 is the initial distance. And that's 0.702. Final distance from start? F of 0.408. And what does F of 0.408 equal? Who would have learned something in this class? You can do it. You can do it.
That's so 0.408 minus 0.4 equals 0.702 times.
So do it all symbolically, right?
Oh
So final distance equals?
my god.
If you're itching to say it, say it.
Would it be the initial plus the change?
Right, so do that symbolically. What would it be symbolically? The initial is? Not x initial, right? These are the distances.
Oh, so F of 0.4
F of 0.4 plus F of 0.4 plus on dx, right? Plus the change. So this is our linear equation, right? It's our linear equation. The final distance from start is the initial plus the change. And so we got it. So we got the initial. So we do the initial, 0.702, plus how much the change, and that gives us that value. Okay, we're knocking on the door of calculus, guys. This is knocking on the door. We're so close.